In the last video, we looked at geometric sequences. In this video, we're going to look at summing a sequence. The summation of a sequence is called a series. In that video, we saw the geometric sequence 3, 15, 75 and 375. These now were the first four terms of a geometric sequence. We knew it was geometric as when we divided 15 by 3, we got 5, 75 by 15, we got 5, 375 by 75, we got 5. So we had a common ratio now, r, which was going to be 5, and we had a first term, a, which was 3. So if we wanted to find the sum of the first four terms, we would simply add these up. So we'd have 3 plus 15 plus 75 plus 375, and we could, of course, add more terms. In general, if we have a geometric series with first term a, common ratio r, and n terms, we can say the sum of the first n terms is a plus ar plus ar squared plus ar cubed, right the way up, dot dot dot, plus ar to the power of n minus 1. So all we're doing now is simply summing these terms. It would be really quite time consuming to sum in this manner for larger series. So instead, what we use is a formula. We say the sum of n terms is a multiplied by 1 minus r to the power of n over 1 minus r, where a is the first term, r is the common ratio, and n is the number of terms in our series. We could take now the sum of n terms formula and write it slightly differently. Sometimes you'll see the sum of n terms as written as a, and then we'll have r to the power of n minus 1 over r minus 1. With this particular one right here, we use this now when the modulus of r, so the modulus of the ratio, is going to be less than 1. We use this one now when the modulus of a ratio is going to be greater than 1. It just means that we avoid any calculations with negatives in them. It really doesn't matter which you use, as you're going to end up with the same answer, but it could be argued using this one now when the ratio or the modulus of the ratio is less than 1 is easier, and this one now when the modulus of the ratio is going to be greater than 1. This is a result that appears in the formula book, and you can simply plug numbers in. Sometimes though, you'll be expected to now prove the sum of n terms. So that's what we're going to look at doing. So if we write out now the sum of n terms manually, we'd have the first term a, the second term ar, plus now ar squared, plus dot dot dot, right the way up now to ar to the power of n minus 1. What I'm going to do is rewrite now the series here, the summation of our series, but multiply through by r to give myself r s of n. That will give me ar plus ar squared plus ar cubed, and then we'll have plus dot dot dot. Then we will have now ar to the power of n minus 1, and then finally plus ar to the power of n. What I'm going to do is call this one equation 1 and this one equation 2. We're going to do equation 1 minus equation 2. So if I subtract now on the left hand side, I've got the sum of n terms minus r multiplied by the sum of n terms. If we just consider now on the right hand side, these terms are going to cancel out. So we can see ar will cancel with ar. We can see ar squared will cancel with ar squared. The ar cubed will quite clearly go with the next one. We will have the ar to the n minus 1 with the ar to the n minus 1. And that will simply leave us now a and ar to the power of n. So we're subtracting here. So what we're going to have then is a minus ar to the power of n. If we factor on the left hand side, we've got a common factor of s of n. That leaves me 1 minus r. On the right hand side, a common factor of a, 1 minus r to the n, and we can simply divide through. So with a bit of algebraic manipulation, we can show now that the sum of n terms can be given as a multiplied by the quantity 1 minus r to the n over 1 minus r. So that's the proof if you were asked to show it. In general though, you will quote these results and simply put in the values of a, which is the first term in the series, R, the common ratio, and then N, which is the number of terms in the series. So let's go ahead and look at summing a basic series. So we might have now a series, we might have 4, then plus, let's go for 12, let's go for plus 36, and then plus 108. So I've been given now the first 4 terms in this series. What I always suggest you do is write down on the left or right hand side of the page A, R and N. Sometimes you'll have S, but in general we want to find these values. A is the first term. We can see quite clearly the first term here is going to be 4. So I'm going to put in 4. The ratio, well, 12 divided by 4 is 3, 36 divided by 12 is 3, 108 divided by 36 is 3. Common ratio now is going to be 3. We're going to sum the first 10 terms, so N is going to be 10. So what we want to do is find the sum of the first 10 terms. So we can use the S of N is equal to A, the first term, multiplied by 1 minus R to the N over 1 minus R. So I'm going to have the sum of the first 10 terms is equal to the first, which is 4, multiplied by 1 minus now the ratio. The ratio is 3, and that's going to be now to the power of N, which is 10. And then this will be now 1 minus the ratio. So it will be now 1 minus 3. So all we're going to do is put this through a calculator. You can see now that I could use any formula. I'm going to get the same result. So if you don't want to switch between the two, you can use any one of these and you'll get the same answer. So let's go ahead and calculate this. So in the calculator, let's put this in. We're going to have now 4, and then we will have now 1 minus 3 to the power of 10, and we will now divide this by minus 2. So let's go ahead and divide that by minus 2, and that's going to give me 118096. So we got 118096. So 118,096. So that now is the sum of the first 10 terms. We simply put this in. And again, if we think we would add 4 to 12 to 36 to 108, we'd multiply this now by 3, which would give us now 324. And you can see after a while, these terms are going to get very big, and we're going to have now the sum of the first 10 terms being 118,096. Okay, let's look at a different example. We might have now the summation, and this is going back to using sigma. Remember, Greek for the sum is sigma. And we might have now R is equal to 1, and then we'll take 1 to 6. And we might have now 3, and then we'll have 1/2 now to the R. Now, it's quite important here, but we don't see R to be the ratio. What I want to do now is dissect this and look at each of these in turn. So what we want to do is find the sum from R equals 1 to 6, 3 multiplied by 1/2 now to the power of R. The ratio in this particular case is going to be 1/2. That's our common ratio. Now, our first term is when R is equal to 1. So let's go ahead and build up now a table. We want the first term, we want the common ratio, and we want the number of terms. So we can see the common ratio is going to be 1/2. In the last video, I introduced now the geometric sequence or series as a constant value that we multiply to some power. If we look at subbing in now 1 for R, that's going to give me 1/2 to the power of 1, which is 1/2. So that means that the first term will be 3 over 2. And we're summing from R equals 1 to 6, which means there are going to be 6 numbers. So let's go ahead and use the sum of n terms. The sum of n terms is A, 1 minus R to the n over 1 minus R. So we want the sum of the first 6 terms, which is going to be 3 over 2, 1 minus now the ratio, which is 1/2 to the power of 6 over now 1 minus the ratio. So let's go ahead and just simply plug this into a calculator, and this will give us the sum of the first 6 terms. So we've got 1.5, and then we'll multiply this now by the quantity 1 minus 0.5 to the power now of 6, and we will now divide this by 1 minus 1/2, which is going to give me 0.5. So we can see that's 189 over 64. So the sum of the first 6 terms is going to be 189, let's write this down, 189 over 64. So all we're doing now, let's just check we got all our values in. We know the first term is going to be 3 over 2, which is 1.5. We've got 1 minus 0.5 to the power of 6 over 1 minus a ratio, which is going to give us 0.5. And that's going to be 2.953125. And that now, as an exact fraction, is going to give us the 189. Let's look at 189 over 64. Okay, let's look at a different type of question. Let's say we were given the third term. Let's write this out. Let's say the third term was going to be equal to 10. Let's say now the sixth term, let's take the sixth term, would be equal to 80. And we want to find now the sum of the first, let's say we're going to find the sum of the first 9 terms. So let's just consider the third term and now the sixth term. What I'm going to think about now is a sub n is equal to ar to the power of n minus 1. This gives me now any term in a geometric sequence or series. We saw this in the last video. So if I think about this one right here, I'm going to have now ar to the power of 5. And ar to the power of 5 will be equal to 80. And I'm going to call that equation 1. So what we've got here now is we're told that the sixth term is 80. So that's ar now to 6 minus 1, which is 5. If we look at this one, this is the third term. So if this is the third term, what we've got is ar squared. And that's going to be equal to 10. And I'm going to call that equation 2. Now, if we divide 1 by 2, we're going to end up now with the a's cancelling. A over a is 1. R to the power of 5 divided by r squared is going to give me now r cubed. And that's going to be equal to 80 over 10, which is 8. Taking the cube root, we can see r, now it's a cube root of 8, and that's going to be 2. So I've found my ratio. So what I'm going to do is start building up these values. Down the side of the paper, I want a, I want r, and I want n. I already know n is 9. We're summing the first 9 terms. I've now got the ratio. All I want to do from this point right here is find the value of a. I know r is 2, so subbing it in here, we've got a multiplied by 2 squared, which is 4, will be equal to 10. So we can see that a is going to be 10 divided by 4, which is 2.5, or 5 over 2. So now we've got our values, and we can simply plug this in. S of n, and I'll show that this can be done either way round. We're going to have now r to the n minus 1 over r minus 1. So in the last couple of examples, I've gone the other way and now used 1 minus r to the n over 1 minus r. Just to switch things around, I'm going this way now. So we can say the sum of the first 9 terms is going to be the first, which is 2.5. The ratio is going to be 2 to the power of 9 minus 1 over the ratio, which is 2, and then we're going to have this minus 1. So straight for a calculator now, this 2 minus 1 is 1, so we can now do 2.5. So we've got 2.5, and then we're going to multiply this now by 2 to the power of 9, and we're going to subtract away 1. And this will give us the sum of the first 9 terms. So that gives me now on there 1277.5. So 1277.5, and that now is the sum of the first 9 terms. So all you're ever doing with this is collecting. You're finding unknowns and you're putting them in. So in this particular case, we got 3 of the known values and we find the 4th unknown. We might be given the sum and we might need to work this backwards. In a later video, we will look at some more problematic questions and some word-based ones that you're likely to get in an exam. So far, these are fairly straightforward to find the values of a, r, and n and plug it in to find the sum. So if we have the sum and we had to find a, we would just go ahead and solve for a by making a the subject. Okay, let's finish with one more question. Let's take one now. For the geometric series, so let's do a geometric series. Let's go for 6 plus, and then we'll have 12.6 plus, and then 26.46, and then we'll have plus ... We're asked to find the greatest number of terms for which the sum does not exceed 1,000. So let's go ahead and think about this. We want to now find the greatest number of terms for which this sum doesn't exceed 1,000. So what we can say then is the following. 1,000, and we don't want it to exceed it, so we can say that 1,000 will be greater or equal than, and I'll just write out now the sum of n terms. So we're going to have a, we'll have now 1 minus r to the n over 1 minus r. So what we need to figure out is a, we need to figure out r, and then we'll look at n. N is what we're solving. So we've now got this sum. So a is the first term. We can see that that is going to be 6. A is now always given to be the first term. If I do 12.6 divided by 6, I'm going to get 2.1. If I want to check that, I could check that on a calculator for the next one. 26.46 divided now by 12.6 should give us exactly the same, and that's going to give us 2.1. That is the common ratio. So we're told it's geometric. We've shown now the first two comparisons give us 2.1, and then we will assume that all the others are if it's geometric. And we're solving now for n. So what we're going to do is plug this in. So we got 1,000 will be greater or equal than, and then we got 6, and that's the value of a. 1 minus now the ratio, which is 2.1 to the power now of n, over now the ratio, which is going to be 1 minus now the 2.1. So this is what we're dealing with here. Now at this stage we can do some calculations from here and now change the inequality round. If we look, what we could do now is multiply both sides by this quantity. Now that's going to give me a negative number. What I could do instead is write this out as 1,000 is going to be greater or equal than 6, and then we're going to have 2.1 to the power of n minus 1 over 2.1 minus 1. So what I've used here now is a, and we've got now 1 minus r to the n over 1 minus r, and in this one I've got now r to the n minus 1 over now r minus 1. And for this particular one, it's going to make it slightly easier. We certainly don't have to, but it might make your work slightly easier. So what we're going to do now is 1,000 divided by, now I'm going to divide this by 6 over now 1.1. So we got 6 divided by 1.1, and we will tidy that up shortly, and that's going to be greater or equal than 2.1 to the n, and then we're going to have minus 1. So let's go ahead and just evaluate this. So what we're going to have, let's put this in. So this is going to be 1,000, and then we're going to have now 6, so let's put 6 over 1.1, okay, and that's going to give me 550, and then we're going to have on there now, that's going to be 550 over 3. I'm going to add 1 to both sides. So if I add 1 to both sides, just adding 1, let's do that. That's going to give me now 555 over 3. So we can write 550, let's check that, 553 over 3 is going to be greater or equal than 2.1 to the power of n. At this stage I want to solve for n, so I'm going to take logs of both sides. So if I take log, and I'll take base 10, really doesn't matter, of 553 over 3, that will now be greater or equal than log base 10 of 2.1 to the power of n. Using log laws, we can bring the n down. So I've got log of 553 over 3 is going to be greater or equal than n multiplied by log of 2.1. If you're yet to do logarithms, this might not make an awful lot of sense. So do check now where this sits in your course, but I assume at this stage now you've done logs. When we're dividing by a logarithm, we just need to be careful. This is base 10. Any number between 0 and 1, excluding 0 and 1, will give us a negative number. Let's just look at that now. If we do now a log of 0.1, this is asking me what power I raise 10 by to get 0.1, and the answer is minus 1. If we're dividing an inequality by a negative number, we need to change the sign around. We know that this is going to be positive as it's greater than 1. So I'm just going to write this as log of 553 over 3 divided now by log, and then we're going to have 2.1 will be greater or equal than n. So let's go ahead and evaluate this now in the calculator. And this time I'm not going to use base 10, I'm going to show that we could use the natural logarithm. It really doesn't matter as long as we're consistent. So 553 over 3, and then we're going to divide this now by the natural log, and we call this the natural log, which is base e, of 2.1. Any base you like, as long as you're using the same base. So for example, you could use log base 2, you could use log base anything you want. So what we end up with now is 7.0312 and so on and so forth. So 7.0312 dot 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 is going to be greater or equal than n. So if we like, n has to be less or equal to this value, and of course we're dealing with an integer as n is now a number in this series, so it's essentially going to give us a term in the series. So what we can say then is n is going to be 7. Let's just go back to the wording of the question. It said for the geometric series 6 plus 12.6 plus 26.46 and so on and so forth, find the greatest number of terms for which the sum does not exceed 1000. So it's going to now be the value of 7. So that is the number of terms. So all we've done is use logs to solve them. So that's a slightly more challenging question. And the main area where pupils come unstuck is when they're dividing through by a logarithm. If you want to just have a play about with this now, if we look, this is log base 10. Log base 10 of 10 is going to give us 1. If we think about log base 10 of 1, what power is 10 raised by to get 1? The answer is 0. Therefore, if we did, for example, the 0.1, that's going to give us minus 1. If we did 0.01, that's going to give us minus 2. This is saying now, what power is 10 raised by to get 1/100th? And it's going to be 10 to the minus 2. So do be careful. If you've got now log of a number between 0 and 1 when you're dividing, the inequality sign will change. So there we go. That's a brief introduction to now the summation of a series. So we're looking at a geometric series and we're looking at the sum. In a later video, we'll work through some word-based problems and some typical exam-style questions. We'll also look at the sum to infinity, but hopefully for now that's given you a good basic introduction.